Hello everyone. Now, in this session, we are going to discuss the frequency dependence of electronic polarizability according with the frequencies. Now, the figure shows that according to the frequency spectrum, the polarization of the dielectric material is to be going to change with each region of frequency. Now, over here, the frequencies are classified according to power, audio, radio, infrared, and optical visible. Whereas in y-axis, the polarization it should be structurized according to electronic, ionic, orientation, and space charge polarization. Now, as we know about that one, where the proportionality of polarizability is only depends upon the electrical field strength with elementary dipole volume. It is an important property of elementary volume of the dielectric material. Now, when polarizability indicates how easily the dipole moment is induced in an atom or molecule by an electrical field of unit intensity. As we know, the frequency dependence of the dielectric material directly in terms of the dielectric structure. As we know, the frequency it should be more important parameter which should be depends on the dielectric constant. When a dielectric material is subjected to an alternating field, the polarization component required to follow the field in order to contribute to the total polarization of the dielectrics. The relative permittivity, which is the measure of the polarization, also depends on the frequency. The dependence epsilon of an frequency of the electrical field means the permittivity of an dielectric material is depends upon frequency of the electrical field. Now, at very low frequency, the dipoles will get sufficient time to orient themselves completely with the field, and all types of polarization exist. Since the dielectric is characterized by polarizability, epsilon in bracket epsilon r is equal to epsilon e plus epsilon I plus epsilon o at low frequencies. That means at radio frequency region, the dielectric constant will be due to all polarizability. The orientation polarization, which is effective at low frequencies, is damped out for higher frequencies, and in the microwave region, the dipole fails to follow the field and the polarizability reduces to epsilon is equal to epsilon e plus epsilon I. As a result, epsilon r decreases to some amount, and this it should be shows in this diagram. The polarization of an electronic, ionic, orientation or space charge it should be only available at the power frequencies applied to that dielectric material. When the frequencies are going towards the further range, that means in audio frequency, radio frequency, infrared frequency or optical frequency, then the polarization level also goes on a decreasing level, and henceforth the epsilon value also goes on decreasing level. Now when an external electrical field is applied, then these electrons are set into the forced vibrations. The molecules in the dielectric material are represented as a dipole or bound charges. Therefore, the number of positive charges should be equal to the number of negative charges to maintain the dielectric material electrically neutral. When an electromagnetic wave is incident on the dipoles, then they oscillate, and before that they radiate an energy. If the frequency of incident electromagnetic wave is not equal to the natural frequency of the bound charges, then the forced oscillations are smaller amplitude and the radiated energy from the dipoles is weak, and at the same frequency as that of the incident electromagnetic wave. This result is a molecule scattering. But if the frequency of incident electromagnetic wave is equal to natural frequency of bound charges, then a resonance should be takes place and a much large energy goes from the electromagnetic wave into the vibrating charge. As we know over here, the frequency dependence of a dielectric constant as the figure shows. The x-axis should be shows the angular frequency of that dielectric material, whereas in y-axis the permittivity of dielectric material should be indicated. Now the output of that dielectric constant should be classified according to the frequencies applied for that dielectric material. Now over here the frequencies in the range of gigahertz and the optical frequencies are to be applied on that dielectric constant. Now over here the permittivity, it should be shows an interface decreases to the orientation level. Also it should be shows that the ionic level and electronic level of orientation, which are more important to indicate the frequency dependence of the dielectric constant. Now this dielectric material, which will be absorb the radiation in the visible and ultraviolet section of electromagnetic spectrum only. Classically, the meaning of absorption is that the electrons cannot follow the electrical field of incident electromagnetic radiation anymore. and this results to the polarization of an electron can be considered to be instantaneous and, more importantly, the independent of the frequency when an absorbing energy of that electrons should be visible and ultraviolet section. Now, the frequency dependence of permittivity, it should be shows that in previous session we are already shows that one the frequency dependence of that material should be related with relative permittivity, and it can be proved that the expression for the complex dielectric constant or relative permittivity is given by epsilon r dash is equal to 1 plus minus n e square divided by m epsilon 0 in a bracket omega 0 square minus omega square divided by minus omega 0 square minus omega cube bracket square plus 4b square omega square divided by m square bracket completed. Again, epsilon r double dash is equal to minus n e square divided by m epsilon 0 in bracket minus 2b omega m divided by omega 0 square minus omega square bracket square plus 4b square omega square divided by m square bracket completed. As we express that one, the equation in the complex form notation continue the real and imaginary part as follows. The epsilon r star is equal to epsilon r dash minus j epsilon r double dash, where epsilon r dash is the real part of this permittivity equation, whereas epsilon r double dash is an imaginary part of this permittivity equation. Now, the real and imaginary part should be consist of the equation. It should be depends upon frequency, and it gives various values according to the condition of frequency it should be applied to that particular dielectric material. Now, when the angular frequency omega 0 it should be applied, the imaginary part epsilon r double dash will be equal to 0. The real part epsilon r dash will be positive for all the values omega less than omega 0, and the real part of epsilon r dash will be negative for all the values of omega higher than omega 0. The permittivity epsilon r is complex because the polarizability alpha is a complex quantity. The polarizability alpha is a complex quantity because the induced dipole moment in bracket alpha e and the polarizations are not in phase with applied field E. Means what? When the angular frequency becomes 0, the imaginary part of epsilon double dash will be equal to 0, and when the omega shows some value, then epsilon r becomes an complex quantity where this complex quantity is induced dipole moment alpha e and the polarizations which are not in the phase with applied field capital E. Now the next point is nothing but the dielectric process. Now an ideal capacitor once gets charged can hold the charge for infinite time. This is possible only if the dielectric used is a perfect one, which means it does not allow any current to flow through it. In other words, the resistance of the dielectric material is infinite. The insulating resistance of any dielectric material is not infinite practically. It is of the order of few mega ohms. The practical capacitor is equivalent to a parallel combination of an ideal capacitor and the leakage resistance of the practical dielectric material, which should be shown in this slide. Now consider a parallel plate condenser filled with dielectric material by epsilon r dash. Let the electrode area be capital A and the plate separation be small d. Now the admittance Y or A of the capacitor for any angular frequency omega is given by A is equal to G plus JB, where capital G and B are the conductance and susceptance respectively. The same equation it should be written in the form of equation such as Y bar is equal to G plus J omega C, where C is the capacitance which may depends on frequency because C is equal to epsilon R A upon D. Now the conductance G equals epsilon A upon D, where sigma is an effective conductivity at the angular frequency omega. The conductance G arises because the conversion of part of the electrical energy into heat, but mainly because of the complex dielectric constant. Henceforth, putting the values of admittance in the equation, we can get Y bar is equal to A upon small d in bracket sigma plus j omega epsilon r dash bracket completed again is equal to A upon d j omega epsilon r into star. That is nothing but the considered equation. Now the same epsilon r dash is the complex permittivity such that the j omega epsilon r star is equal to sigma plus j omega epsilon r dash and epsilon r star is equal to epsilon r dash minus j sigma upon omega again is equal to epsilon r dash minus j epsilon r double dash. Should be considered as equal to epsilon r star divided by delta. Now epsilon r star is equal to sigma upon omega. Thus the absorption of the energy by the material in an alternating field is proportional to the imaginary part of the dielectric constant. The dielectric is said to have losses which are characterized by the loss tangent. Now, as we know, the epsilon r is nothing but sigma upon omega. Means what? The relative permittivity of that dielectric material should be depends upon the conductivity and the angular velocity of that capacitance value. Now, the dielectric losses should be measured or should be calculated with the help of the conductance value as well as the angular frequencies value. Now, due to the finite value of leakage resistance in the practical capacitor, which should be calculated with the help of the sigma. The leakage resistance will discharge after some time, and the time depends on the value of that leakage resistance should be depends on the capacitor's value. Therefore, the practical capacitors are called leak capacitors. For alternating voltage applied across a capacitor, the value of leakage resistance becomes the frequency dependent. Hence, there is a molecular friction taking place inside the dielectric material which results in a loss called as the dielectric loss. With the help of this equation, we can conclude only thing is that when a practical dielectric material is placed between the parallel plate capacitor, then the friction between that molecular materials results in loss of a resistance value, and that resistance value should be affect on the capacitor's value, and henceforth it should be called as a dielectric loss. Now, the value of that dielectric loss should be calculated with the help of loss tangent and power factor. Now, the next point should be related with loss angle and power factor of capacitor. As we know, the capacitance of a capacitor is not perfect and constant at all the frequencies due to the several effects. Now, these effects include the ohmic losses taking place in the capacitor plates and connecting wires, or polarization, and power loss takes place in capacitor dielectric. We can represent the capacitor with all these effects with the help of equivalent circuit diagram as shown in the slide, where the conductance and capacitance are connected parallelly with applied voltage V. Now, for the capacitors, air dielectric, the dielectric loss is very small. Hence, the air dielectric capacitors are considered to be a perfect one. But when a solid dielectric it should be placed within that parallel plate capacitor, then the phasor diagram of that capacitor it should be shown in the figure or in the slide in right hand direction. Over here the V is applied across the capacitance and conductance. Due to the voltage applied, the total current I should be flows through that circuit. The total current I should be split in the capacitance and conductance value, and according to that one the phasor diagram should be drawn. Now the current flowing through capacitor and the current flowing through that resistance should not be in phase with each other. Due to that, the power factor has been introduced in the dielectric material as it should be given by the power factor is equal to cos phi. But over here phi is nothing but 90 minus delta. Therefore cos phi is equal to cos 90 minus delta is equal to sin delta, where over here the delta is called as a loss angle of the capacitor, and the value of that delta is very small. So that we can calculate the dielectric loss with the help of the equation that the dielectric loss is equal to Vi cos 90 minus delta, which is again equal to Vi sin delta. Further solving this equation, we can get dielectric loss is equal to V divided by IC upon cos delta into sin delta. It becomes Vi tan delta, and the final equation for that power loss or dielectric loss should be nothing but Vi tan into delta. Now the loss angle and power factor of that capacitor, it should be indicates that in the circuit the IC is the conduction current which is responsible for the dielectric losses and is in phase with the applied voltage, whereas the ID is the displacement current which is in the phase with quadrature of the applied voltage. Now I is the phasor sum of IC and ID. If there are no losses, epsilon r double dash is 0 and current I leads the applied voltage by 90 under these circumstances. So now according to the power factor and loss angle, we can conclude that the quality of a capacitor is indicated by the value of its power factor. When the power factor is low, ideally it should be 0 for a capacitor, but it indicates a small dielectric loss and a small leakage current with a small loss angle of delta. It has been observed that the power factor or tan delta remains constant over a wider range of frequencies. Therefore, the tan delta is also called as the dissipation factor D of capacitor. So, the dissipation factor, it is also called as loss angle of the dielectric material. The dissipation factor D is equal to tan delta. Next point is nothing but the significance of loss tangent. The loss tangent has a very small value for free space, and for solid dielectric material, tan delta is nothing but 0.003, which is equivalent to Q of 300, Q of 3000. So, a fairly good value of Q for a coil is around 300. That is why we attach the importance to losses in a coil and ignore those in capacitors. The variation of tan delta with the frequency will show a normal resonance like behavior, and this is shown in figure below. Over here, the frequency should be indicated according to the x-axis, whereas in y-axis the tan delta or the loss angle should be indicated. Now, according to the frequencies, over here the tan delta, the smaller portion having the big value of loss, it should be indicated over here. Now, according to that one, the relative permittivity, it should be shows the constant value, and when the tan delta, the smaller loss should be indicates, that should be nothing but the epsilon r value goes to the epsilon infinity with the loss angle effect, and it should be still continues to the further frequencies. Now, the curve of tan delta has the largest value in the region of frequencies where there is a sharp change in the dielectric constant. In case of ionic resonance, this change in the dielectric constant occurs from microwave to infrared regions of frequencies. The dielectric losses associated with ionic vibrations are usually referred to as infrared absorption. Similarly, the losses in the optical region associated with electronic vibrations are referred to as optical absorption. Hence, it is possible to predict whether the dielectric properties are due to ionic or electronic polarization. The occurrence of absorption in the optical region is the source of color in the materials. For example, NaCl is transparent in the visible region, which means that there is negligible absorption for the corresponding frequencies. Under X-rays, NaCl turns yellow to brown. So, up to this part, we have studied that there are frequency dependent on permittivity. Then we have discussed about the various loss angles, power factor of capacitors, loss tangent, dissipation factors, and all other concepts regarding with the dielectric material. So up to this point, we have discussed about the various parameters or the various specifications of dielectric material. Okay, today's session we will be concluded over here. If you have any query, kindly reply with any queries, ask the questions so you can understand it should be better.